So, so let's just continue from where we left off, but maybe before that, a quick recap of what we did in the last lecture. So what I showed you in the last lecture was that even if you take a model which you might think is nominally completely classical, it actually still does give you quantum evolution if you interpret the quantities in that model as operators that act on an appropriate Hilbert space. And so the specific model that we looked at was this very simple model of two spins with, Z, with that Hamiltonian. And so you would nominally have thought that this was a classical system, but the whole point is that if you interpret these as quantum mechanical operators, as the Z component of the spins of spin half objects, then it automatically becomes a quantum Hamiltonian. And the quantumness of this really comes out when you look at how it acts on allowed states in the Hilbert space. And so in particular, what we saw was that if you take this Hamiltonian and you evolve an initial state of this form with this Hamiltonian, then something non-trivial happens. And the thing which is non-trivial is that you generate entanglement between these two spins. On the other hand, we also saw that classical information doesn't actually spread to the extent that one can even talk about spreading in a two-side Hamiltonian. And so that was reflected in the fact that if you were to calculate the expectation values of the x component and the y component of the first spin as a function of time, then these do not depend on the initial expectation values of the x and y components of the second spin. They only depend on the expectation value or the value of the z component of the second spin, and that object is something which isn't evolving as a function of time because it's a constant of motion, because it commutes with the Hamiltonian. But the other quantities which could in principle have affected this evolution do not affect the evolution in this particular case. And so that's so the expectation values of these operators are what I called classical information in the last lecture. And the reason that this is classical information is that if you wrote down the corresponding classical model, then the only quantities in the classical model are actually those which correspond to these expectation values. There is no equivalent of this kind of state in the classical model. Okay, and then having sort of looked at this simple Hamiltonian in a certain amount of detail, what we ended up doing towards the end of the last lecture was now looking at a Hamiltonian which involves more sites. And so something which has the following general form, so summation over I and j okay, and so the interpretation of this is that there's a 1D lattice of sites. Actually, it doesn't even have to really be 1D, but for what I'm going to tell you next, it's best to think of this as a one-dimensional lattice. And so imagine that you have a one-dimensional lattice and you have these spin halves at every site. Okay, I'm just sort of schematically drawing spin halves, but these are quantum mechanical spin halves. Then, so you have these spin halves at every site, and the Hamiltonian of the system is this. So it's only the z components of these spin operators which couple. And in principle, you have a coupling between every pair of spins I and j with a coupling strength that we assume depends on the distance between I and j. Okay. And so this, you can see, is sort of a generalization of this Hamiltonian, of the simple two-side Hamiltonian, to include more sites. And then what we saw was that even for this Hamiltonian, even though there are more sites as a full lattice on which this is defined, there again is no spread of classical information, and that we realize by looking at the operator equations of motion for this Hamiltonian. And so the operator equations of motion, so if you look at the operator equation of motion for, say, a spin at site I, then this is the operator equation of motion, which is also what you would get if you assume that the system was completely classical, and instead of operators, you actually had the appropriate components of the spin. And so the HI, this magnetic field here, like we saw in the last lecture, is that quantity. And so just like in the two-side problem, even in this case, what happens if you want to think of the system physically is that the spin at a particular site I, Larmor precesses, so it undergoes Larmor precession about a magnetic field generated by the Z components of the spin at all other sites. And so once again, if you look at how one of these spins is evolving, the x and y components of the other spins don't affect the evolution of this particular spin. And so again, there is no spread of classical information, because like we discussed in the last lecture, a spread of classical information would have meant that if, let's say, your initial condition was such that there's one particular spin which had an unusually large parallel component of the spin as compared to the other ones, then if that classical information was spreading, then the other spins would get to know about this fact, meaning that somehow this information about one particular spin having an unusually large parallel component would then diffuse out into the rest of the system, and that does not happen here. So there is no classical spread of information, but what we do expect is, just like in the two-spin case, there is going to be a spread of quantum information. So in the two-spin case, the way that the quantum information spread was that if you start that system out, the two-spin system, with an initially unentangled state, the one which I wrote down, then as the state evolves, the two spins get entangled. And so if you want complete information about the state that you get to at some time t, if that's what you want, then what you have to do is you have to actually make non-local measurements or calculate expectation values of non-local operators. And that is how you have a spread of quantum information, that even if the initial state could have been completely arrived at by making local measurements on each of the spins, as time evolves, as time progresses, you would have to make non-local measurements in order to get information about the complete state. And so this quantum information in this sense is now spreading. It's becoming more and more non-local. And so if you have a system like this with many sites along the lattice, then of course you would expect to see a very sort of large spread of quantum information. So as time progresses, you should have this notion, and we'll sort of make this a little more concrete as we go along, that the quantum information, the amount of quantum information as quantified by this kind of spread is going to increase with time. And so that's what we're going to look at. So as far as comparing quantum and classical states goes, a classical state in a quantum mechanical description for us is a product state. So that state that I wrote down up there is a classical state because it's a product of the state of the first spin and the state of the second spin. So the state gets more and more quantum and less classical as you deviate from this particular product form of the state. So for instance, what we saw is that if in the two-spin case, if your initial state is the one that I wrote down earlier, then the state at some time t is cosine omega t times the initial state, but then I forget if there's a minus sign, minus I sine omega t times the other state. And this state can't be written as a product of a state of just the first spin and the second spin. So you can ask, well, how do you quantify this? How do you quantify how far away a given quantum mechanical state is from being a product state, from being a classical state? And so the most common way of doing that, and in some sense also the most sort of reasonable way of doing it, is by defining something called an entanglement entropy. Now, during the school, I guess you've already heard about the entanglement entropy several times. So I'm not going to spend too much time on trying to motivate where it comes from. Instead, I'll just tell you, just write down a few expressions which have to do with how you calculate the entanglement entropy and what the basic idea is. So the basic idea behind quantifying how far a state is from being a product state using the entanglement entropy is that you take your system and you partition it into two parts, A and B, and in principle, depending on the context, A and B could be any way of partitioning the Hilbert space of the full system. But how you partition it depends on the specific context. Also, whether the state looks entangled or not also depends on how you're partitioning it, what kind of basis you're choosing for the Hilbert space, and so on. So for us, the natural partitioning is going to be, because we have a one-dimensional lattice, what we can do is we can just take the lattice and split it. So assume that we have, say, an infinitely long chain of spins. It's an infinitely long lattice, and so what we can do is we can make a partition somewhere, split the lattice into two semi-infinite halves, and then look at the entanglement between these two semi-infinite halves for the full system in a given state, and that's going to be our entanglement entropy. And so the way that the entanglement entropy is calculated for a given state of the full system is that if the state of the full system, so state of the system, and by system I mean the combination of A and B, in set theoretical terms, if you like, A union B. So if the state of the system is psi, then the prescription to calculate the entanglement entropy is that you first define a density operator for the full system constructed from this pure state. So that is the density operator of the full system. And then what you do is you construct what's called the reduced density matrix of either half. So the reduced density matrix say of this half, rho A, is a trace over the degrees of freedom of the other half of the full density matrix. So you can construct the reduced density matrix for the half A, or you could also construct the reduced density matrix for the other half B by performing a trace over A. And these two reduced density matrices don't have to be the same. In fact, they will not in general be the same, because these two Hilbert spaces also don't necessarily have to be the same for a given system. However, the object which does end up being the same, regardless of which density matrix you're constructing it from, is the entanglement entropy, which is defined as, so if you're using this density matrix, it's now a trace over A of which is also equal to this. Okay. And so now what you can do is you can convince yourselves, if you haven't seen this sort of thing before, that if the state in question was a product state of A and B, then the entanglement entropy is equal to 0. On the other hand, if the state in question is some superposition which cannot be factorized into a product, then the entanglement entropy is non-zero. And in fact, you can also convince yourselves from these definitions that the largest value of, okay, so does anyone actually know what the largest possible value of the entanglement entropy can be for any state? So imagine that, I have a system, I partition it into two Hilbert spaces A and B, and then I'm looking at some state of this combined system. What is the largest possible entanglement entropy? Does anyone know? So louder? Okay, log of n, but what is n? So the full system, let's say, has a Hilbert space dimension n. Is the n in your answer that Hilbert space dimension, or is it something else? So the answer is that the largest entanglement entropy possible is the log of the Hilbert space dimension of the smaller of these two spaces. Okay, so that's the largest value of the entanglement entropy that you can get. Okay. And so the smallest value is 0 if you have a product state. The largest value is the log of the smaller Hilbert space dimension. And anything which is non-zero tells you that the state is entangled. And the larger the entanglement entropy is, in some sense, the more entangled the state is. So a couple of remarks about the entanglement entropy before I show you, what happens for the kinds of systems that we've been looking at. So one thing about the entanglement entropy is that even though the entanglement entropy is quantifying, in some sense, the amount of quantum information in the system as given by how far it is from being a product state, knowing the entanglement entropy by no means tells you what that state actually is, right? Because it's just one single number that you're extracting from the state. So for instance, if you remember in the last lecture, for two spins, we considered a state like this. So for this sort of state, if you had to calculate the entanglement entropy, meaning the entropy of entanglement between this spin and this spin, does anyone know what you would get if you, for this particular state, if you dealt, so log 2, okay. And you'd get log 2 regardless of what this theta is. So once again, the entanglement entropy is not going to give you anything like complete information about the state because it's just one number. So that's one thing to keep in mind, that it serves a very specific purpose. You're not going to get everything, all the information about the state from calculating this. The other thing to keep in mind, and this is just a remark that I'm going to make, not that I'm going to use this concept, is that so this is a good way of looking at deviations from the product nature of a state only if the state of the system, of the full system, is a pure state, okay? If you have what's called a mixed state, and we'll worry about mixed states in my last lecture when we look at open quantum systems, and where the state of the full system is given by a density matrix, then of course it turns out that this way of trying to quantify how far the mixed state is from being a product of two mixed states is actually not the right thing to do. Meaning that you could have a state in which the state of the full system that's described by a density matrix, and that density matrix could be factored into a density matrix for state A times a density matrix for state B. So it would look like a nice product state in terms of these density matrices. But if you were to calculate the entanglement entropy in this way for that mixed state, you would actually get something that's non-zero. And so when you're dealing with states of the full system which are not pure states, then it turns out that the entanglement entropy is not a very good measure of how truly entangled these states are, how far away the state is from being a product state. And then there are other measures which people use, which some of you, if you've taken the right kind of courses or if you've been working on this kind of stuff, would know. So there are things like something called the concurrence, and then there's something called discord and so on, which are all measures of the sort of quantumness in a more general context. So I thought I'd just mention that to you, but I'm not going to dwell on that anymore. Okay, so this is the entanglement entropy, and so for this particular state, so as an exercise now, given that we have this definition of the entanglement entropy, so as an exercise I would urge you to calculate the entanglement entropy for this state psi of t, which is obtained from the evolution. Okay, so for going back to our two-state system, our two-spin system, if the two-spin system starts out in this initial product state, right, then the state at any time t is just given by that, and we've already written down an expression for this unitary. So as an exercise, I would urge you to calculate the entanglement entropy of this state as a function of time. So you'll see that the entanglement entropy, of course, has to start out being 0 because it's a product state, but you'll see that it has some nice oscillatory features. So this does indeed entangle the two states. And so when you do this calculation, what you will find is that the entanglement entropy, and I'm not going to write down the exact form because I want you to work it out, but the entanglement entropy is going to be a function of, clearly a function of jt by h bar, because that's really the only parameter that you have in the problem. And so it's going to be some oscillatory function. So in some sense, what you could say is that the entanglement entropy starts out being 0 at time t equal to 0, and then it oscillates as a function of jt by h bar. And so the relevant time scale over which the entanglement entropy reaches some value, let's say the maximum value that it can reach for this state. So that time scale for the evolution of the entanglement entropy in this simple case, for the evolution of S, is h bar divided by j. So that's your time scale. So over this time scale, there's some oscillations which happen, like, this is like the period of the oscillation. So over this time scale, the entanglement entropy reaches a maximum and then again goes to a minimum and keeps oscillating. Fine. So the reason that I mentioned this is that given all of this, we are now in a position to at least try to semi-quantitatively, mostly qualitatively understand what happens to the entanglement entropy for the Hamiltonian that I wrote down for a chain of spins. Okay, so given that this is what happens for two spins, now let's look at what happens when you have a chain of spins. So our Hamiltonian for the chain of spins is I minus j and wait, sorry, let's write this here. Okay, so to investigate what happens with the entanglement entropy, let's do the following. Let's start this system out in a state which is a product state of the spins at every site in the x direction, just like we did for the two-spin problem. So suppose this is the initial state. And now you can ask, well, how does this state evolve as a function of time given this Hamiltonian? Now, you can, in principle, write down what the unitary of this is. So if you wanted to do that, then the unitary of this system would be this object. Right? And so the idea behind this is that when you're raising that Hamiltonian to an exponential, because every term in that sum commutes with every other term, you can write down the exponential of that sum of terms as a product of the exponentials of each individual term, which is what I've written there. And then, of course, each individual term now is a two-spin term. And so for each individual term, we can write down the unitary that we'd written down for the two-spin Hamiltonian. And this is just going to be a product of all of those. So in some sense, writing down the unitary in this sense is simple. But then doing any calculation with it and actually obtaining the state, the evolved state starting from that initial state and seeing how that evolves as a function of time, and then doing any explicit calculation with that state is going to be hard, because you can see from this, because you have a product of these unitaries, each one of them is going to give you, so if you look at a particular term so when you expand that product out, so this unitary is going to be a sum of many, many terms. And if you look at any one particular term in that sum, it's going to be some trail of these SZ operators over some number of spins, and not even necessarily a contiguous trail. And the sum is going to be and the unitary is going to be a sum over all such terms. And what these terms are going to do when they act on the initial state is they're going to cause these spins to flip from right to left, because that's what the SZ operator does to an eigenstate of the SX operator. And so at any given point of time, you're going to have a very large superposition of states, of these product states, with the spins pointing in, some number of spins pointing in the x direction and some number of spins pointing in the y direction, but all such combinations. And so you can see that that's a fairly entangled state, but it's something that's difficult to do any proper calculations with, any exact calculations with. So instead, to find out what actually happens to the entanglement as a function of time, let's just proceed in a slightly heuristic way. So first of all, to make things concrete, let's just make an assumption for, like I discussed in the last lecture, for what this is doing as a function of mod I minus j. And so let's assume that this goes as some j naught into e to the power of mod I minus j by some length scale c, and this is, it's a length scale that's associated with the way in which the coupling is falling off with distance. Okay. And so, in principle, as I said, we can stick this in here, write down this unitary, but it's not going to be of much use to us to calculate the entanglement entropy exactly. Instead, what we can do is we can actually resort to what we've learned from the two-spin system. So let me just draw a few pictures first to show you what's happening. So at time t equal to 0, what we have is we have a state which is completely unentangled. It's that one. So I'm just going to draw that state in this way, with each dot on the lattice representing a spin. And this picture with these dots is supposed to tell you that at time t equal to 0, there's a state of this spin here, state of this spin here, state of this spin here, and you have a product state. Now suppose we evolve the system a little bit. Suppose it evolves for a certain amount of time. Then of course, we no longer have this product state. We're going to get an entangled state. But you can ask, well, in that entangled state, right, how much of the amplitude is still in the initial product state, and how much of the amplitude has spread to other states, and what is the amplitude that is spread to other states? And so that is where the exponential nature of this coupling becomes important, because you can see that from our experience with the two spins earlier, that you end up getting a superposition, a non-factorizable superposition between two spins over a time scale which is like the inverse of the coupling between those two spins, right? And you can see that the coupling is actually falling off exponentially. So if you evolve the system for a short amount of time, then sure, the amplitude from this state is going to go away into other states, but the state which will have the most amplitude, aside from this one, is going to be the one in which you're going to have a coupling, you're going to have entanglement between nearest neighbor spins, because the nearest neighbor coupling has the largest amplitude. So in the shortest amount of time, you're going to have an appreciable coupling and appreciable entanglement over those spins. So if you evolve the system now for a short amount of time, let's say at a slightly later time, t equal to t1, then what will happen just schematically is that your state is going to, of course, you'll still have this will still have most of the amplitude, but then the remaining amplitude will mostly be, the remaining amplitude is mostly going to be over states which will look like this. So let me just draw a section of, so you're going to have some state where, let's say, these two spins are entangled, plus a state where those two spins are entangled. Of course, this is only a small section of the whole lattice. So basically, a superposition of those states of the whole lattice which involve entanglement only over one particular pair of spins, and all such superpositions with some amplitude. That's not to say that the other terms are not there. I'm just saying that this is going to be the next dominant term after the original unentangled state if you evolve the system for just a short amount of time. And so, again, let me just draw another one. So there's this, there's this, there's this, there's this, and so on. Okay, so that's at time t equal to t1. And then if we evolve the system for a little more time, then what's going to happen is that the coupling between next nearest neighbor spins is also going to become appreciable enough, or rather the coupling between the next nearest neighbor spins is now going to kick in. And so over this amount of time, a little more time compared to t equal to t1, you will now start developing entanglement between next nearest neighbor spins. So if you had to write down a schematic of the state at that time, then it would be this plus this. Remember that this entanglement is not going away anywhere. This is still there. It's going to be this plus this, but you're also now going to have an appreciable weight over states which involve entanglement over next nearest neighbor spins. So something like this plus something like that, and then I don't know, maybe and so on. And so as time progresses, what you will see is that you will have more and more amplitude getting distributed into states with farther range entanglement. Okay, so you draw a schematic like this of the state, and you can ask, well, how does the schematic help us in calculating the entanglement entropy, or at least arguing what the, or at least coming up with some form for what the entanglement entropy would be. So just using the argument for the two-spin model, so the entanglement entropy, or the entanglement rather, over some distance L becomes appreciable. So the entanglement over a distance L becomes appreciable at a time t when j e to the power of minus L by C t by h bar is of order 1. Right? And so from this you can see, so this is something of order 1, that is when this particular the entanglement over this length scale becomes appreciable. And so that immediately tells you what the relationship should be between L and T. So this gives you a relationship between L and T, which is L going as log T. Okay? So after some time T, you're going to have appreciable entanglement, appreciable superpositions if you like, over spins which are separated by a length L. So imagine that at that time t, you're making a cut somewhere in this system. So you make a cut, say, here. Okay, in some schematic way. And you want to now measure the entanglement entropy, or calculate the entropy of entanglement between the two halves. So very crudely speaking, that's just going to be equal to the number of these loops that I've drawn to denote entanglement between pairs of spins, a number of such loops that you cut, right, when you're making this cut, the number of such loops that you actually go through when you're making this cut. And so if the entanglement at that time t is over some distance L, then the number of such loops that you're going to cut is also going to be of order L. And so therefore, this L that we have is proportional to the entanglement entropy at that time t. And so the entanglement entropy itself, S of t, is also going to go as log t. So if you have a Hamiltonian which is of this particular form, so note that this argument for the log here is crucially dependent on our assuming that the coupling is falling off exponentially with distance. If we didn't have that, if we had some other dependence of the coupling on L for this kind of Hamiltonian, then of course we wouldn't get log t. And if you had, for instance, a coupling which fell off as a power law, then you can see that the relationship between L and T would also be some kind of power law then, and you would have a much faster growth of entanglement, which is what happens in systems with long-range interactions of the sort that Michael Kastner told you about. I think he probably might have even explicitly shown you how the entanglement grows as a function of time for his long-range systems. But here we just, using this as an illustrative example. Okay. So if you then had to plot, sorry, did someone have a question? Yeah.
I do not understand the word appreciable.
Sorry?
I do not understand the word appreciable. What do you mean by that?
You don't understand the?
word appreciable, I mean.
Appreciable, okay. So the word appreciable here means that, okay, so just to understand what appreciable means, let's just go back to our two-side system. So for the two-side system, so our state psi t equal to, sorry, psi of t is this, right? So if you ask what happens at t equal to 0, at t equal to 0, this term is 0 and this term is 1. So all the weight is in this state, right? Now as time increases, you will have weight, and remember the state has to be normalized, right? And you can see that this state is normalized. So as time t, as the time increases, what's going to happen is that you will have a transfer of weight from this state to this other state, which is orthogonal. So you can ask over what time scale will the weight for this state become, say, comparable to the weight of this state. So that is when you have an appreciable amount of weight that has been transferred from here to here, an appreciable amount of amplitude which has been transferred from here to here. And you can see that that time scale is going to be something where omega t is going to be of order 1. Now you can ask, well, what do you precisely mean by appreciable? Does it have to be 1/4 of the weight? Does it have to be 1/8 of the weight? Does it have to be half the weight? But that's not really important, because no matter how you define it, whatever you mean by appreciable, ultimately the time scale involved is going to be, when omega t is going to be of order 1, what that precise number is, when I say it's of order 1, right, but what that precise number is will of course depend on what weight you say is the appreciable weight. So that's what I'm saying. So it's just, so the important thing is the time scale. Okay, so therefore, so what will happen here is that for this, so by the way, even though I've used an initial state which was all the spins pointing in the x direction, or having a projection of 1/2 along the x direction as the initial state, this would work. This argument would work for any product state, any arbitrary product state that you start with, unless it just happens that your product state is such that all the spins were pointing in the z direction. Because if all the spins are pointing in the z direction, or a very, very large number of spins are pointing in the z direction, then of course there's hardly any evolution of the state, because the z direction is the direction which commutes with the Hamiltonian. The spin along the z direction is a direction which is the spin operator which commutes with the Hamiltonian, and so there's going to be no evolution of the state. But that's not an arbitrary initial product state, that's a very special kind of initial product state. For an arbitrary state, you're going to have this evolution, and s of t is going to go as log t. What the prefactor is, so you can see that here I'm being cagey about the prefactor. The specific prefactor is of course going to depend on details like what the value of this length scale is, what your initial state is, but that's not important for us. What's important is the way that the entanglement entropy is scaling with time, and it's scaling as log t. Okay, so if you were to just plot this as a function of t, you'd see that the growth would be logarithmic, and so this is log t. And of course the point, yeah.
So is it right to say that every time you start from a product state, so your entanglement entropy behavior just depends upon the time scale?
It just depends on the
time scale of the Hamiltonian.
Right.
Time scale of
Yeah,
information.
yeah. I mean, I'm saying that anytime you start with a product state, right? Of course, the reason you start with the product state is that it's one of the most extreme kind of states for which the entanglement entropy is 0. So you're starting with a state with 0 entanglement, and you're asking how the entanglement is increasing as a function of time, and it's going to increase as log t, something times log t. But what that something is will depend on specific feature, what particular state you're starting with, and also in this case, what the value of that length scale is, and so on. But the universal feature here for Hamiltonians of this sort is this log t growth. Okay, so it's going to grow as log t. Now, if you assume that the system is finite sized, that it's not really an infinite sized system, that it's a system of size L, and you're cutting that system of size L into two segments, each of length L by 2, then of course what you know is that, so if you just look at this formula again, then you know that this L can't be any larger than the length of the system. And so once you reach a time scale which corresponds to this L being the length of the system, there is going to be no further increase in the entanglement entropy, because that's as far, that's the longest range over which anything can get entangled in the system, and then beyond that there's nothing that can happen. And so if you have a finite size system, then what will happen is that you'll have this log t growth, but eventually you're going to have a saturation of the entanglement entropy, which is going to be proportional to the length of the system. So that is the expectation from this sort of heuristic argument. We haven't done any rigorous calculation anywhere, right? This is just some heuristic argument, but that's what we get. So now you can say, well, what happens if you actually do a proper calculation? Right.
So in your time scale analysis, it should be J0, right?
The time scale should be what?
J0, not just J, right?
Wait, so
you have defined the J.
Yeah, so there's a J0 here.
Yeah.
Right.
And another question is that if I have some other distant dependence like a power law, then the same kind of scaling analysis is valid.
No, so that's what I said, right? I mean, at least in this argument, the reason that we get the log t is that this is exponential. If you didn't have an exponential here, if you had a power law, right, say something like L to the power of alpha, so then you can see that you're going to get a different dependence. You're going to get t going as L to the power of minus alpha, and so the entanglement entropy would then also grow as a power law in time. Yeah.
So,
Okay.
just one question. So, does one know the time scale over which it saturates?
Okay, right. So the time scale over which it saturates is going to grow exponentially with the system size, right? So it's going to saturate over a time scale which is exponentially larger than the system size. So anyway, so the thing which I wanted to sort of emphasize is that all of this is basically coming from some heuristic argument. We haven't done any proper calculations because it's difficult, even though the Hamiltonian looks deceptively simple, it's difficult doing an exact calculation with this Hamiltonian. So the best thing that you can do is you can actually do numerics. And so this is the result of a numerical calculation on this kind of Hamiltonian. The only difference here is that the Hamiltonian considered in this paper doesn't just have, doesn't just have this 2-spin term, which is what we've considered, but it also has a 1-spin term and it also has a 3-spin term. Now the reason that the Hamiltonian in this paper has all these terms is because the main goal of this paper was not really only to verify this log t and linear increase of the entanglement with the system size. There's also something else that they were doing for which it turns out that this kind of term is actually important. Regardless, everything that we've said here also goes through for this kind of Hamiltonian, because the only thing that we've assumed in this whole discussion is that the Hamiltonian depends on the SZs, that it's got terms which are basically functions of this SZ, and then there is some notion of a coupling which is falling off exponentially with time. Even if that coupling wasn't a 2-body coupling, even if you had a 3-body coupling. So for here, for instance, you can see how these couplings are, not falling off with time, falling off with distance. You can see how these couplings are falling off with distance here. And both for the 3-body coupling and the 2-body coupling, you have an exponential fall off with distance. And just for the sake of simplicity, they assume that in the length scales involved in the fall off are the same for both kinds of couplings. So this is a numerical calculation for systems of these system sizes, starting from 12 going up to 28 of these one-dimensional systems, and entanglement entropy as a function of time, starting from some random product state. And sure enough, you can see that both of these features that we argued for are present in the data. It just turns out that it's not log t all the way down to t equal to 0 because of the presence of this term. So I'm not going to go into the details of how this term initially affects the entanglement so that you get something other than log t. So if you have a one-body term which has randomness in it, then you basically have this phenomenon of what's called single spin localization. And so the single spin localization, which was not there in what we did because we didn't have a one-body term. So it turns out that the single spin localization initially gives you a growth that is different from log t, and in fact a growth that has no dependence on the system size. But then once the two-body term kicks in and the higher body terms kick in, that's when you start seeing the log t. So the log t is something that you see here. So this is a semi-log plot. So let's say starting from about 10 to the power of 1, and then depending on system size going up to 3 decades or 4 decades or something. So you see this nice log t behavior. And finally, you see this saturation. And in the inset, you have a plot of the saturation value as a function of system size. And you see that at least, given the range of system sizes that they can do the calculation for, it's a nice linear dependence on system size. So this is a very simple model which might look deceptively classical, but actually does have interesting quantum dynamics in it. And the quantum dynamics is represented by this growth of the entanglement entropy as a function of time. It's this logarithmic growth. So by the way, you can see that this paper is actually a very recent paper. It came out earlier this month. And so there's still aspects of this kind of growth in these sort of classical systems of the entanglement entropy and other things that people are actively interested in. So this is not just some toy model only for illustrative purposes for a school. I mean, it actually is something that people are, whose physics people are actually worrying about right now. Okay, so this is as far as this kind of model with just the SZs in it are concerned. But this is not the generic situation, right? Because this is a very special kind of model in which you have no spread of classical information, but you do have the spread of quantum information in the form of the entanglement growing as a function of time. But the more generic situation is one in which not only do you have a spread of quantum information, you also have a spread of classical information. So to give you an example of such a model, and I think I alluded to this in my previous lecture. So suppose we consider now, instead of an Ising type model, if we consider a Heisenberg type model. So now let's say we have a Hamiltonian. And again, just to keep things simple, sorry? Yeah, so those lines, yeah?
The horizontal lines,
yeah,
and the dots, like
yeah,
triangles, and
right.
What are those?
Oh, these horizontal lines, and okay. So you mean these horizontal lines, like this one and this one? So those are just basically indicating the saturation values of the entanglement entropy. So each one of these curves is for a different system size. So if you look at the yellow curve, for instance, it deviates from the log t behavior and starts saturating here. And so this yellow dotted line is the saturation value for the L equal to 12 curve. Then this dotted line is the saturation value for the L equal to 16 curve, and so on. And it's these saturation values which have been plotted as a function of L in the inset to show you that it's actually saturating to something that's linear in the system size. Okay, so now let's look at a much more generic model where the coupling is not just between the z components of the spin, but you have a coupling between all the different components of the spin. And so this is the Heisenberg model, something which I'm assuming all of you are familiar with. And you can think of both the classical version of this model and also the quantum version of this model, with in the quantum case, as for this other model that we considered, the spins being spin halves. So if you write down the equation of motion for either the operators in the quantum case or for the spin components in the classical case, so here what you're going to find is that the equation, so let me just write down the equation of motion for the quantum mechanical operators, and you have exactly the same equations of motion even classically for the spin components. So once again, you're going to get something which looks like this, but there's now two significant differences. So let me just write down the expression for hi hat. So this is equal to summation over j okay. So again, you would say that what's happening here is that you have a precession of the spins, except that this time you don't really have a precession of the spin, because for the spin to precess, like in the previous case, there had to be a constant magnetic field at the location of the spin, and in the previous case that constant magnetic field was given by the z components of all the other spins, and those z components were constants in time. Here that's not the case anymore, because the magnetic field that you have, the local magnetic field that you have at any site I, actually depends on all the components of all the other spins, and none of those components is actually conserved by the dynamics. So it's not like in the previous case where the z component of each spin was conserved, and so you had a constant magnetic field around which the spin was precessing. That isn't happening anymore. And so this is a model for which there really is no conservation law for any particular components of the spin at every site. So as a result of that, if you write out these explicitly, you can easily see that it's no longer the case that, say, the parallel components of all the other spins don't influence the evolution of a particular spin. In principle, every component of every spin is now going to influence the evolution of every other spin. And so this is a model in which you actually do have a spread of classical information, because things are not just precessing and parallel components are not just confined to an individual spin. So here, if you did what I described in the previous case, which is that you start the system out in an initial state such that one spin has a very big parallel component and the other ones don't. For this model, generically what you would expect is that that parallel component is going to diffuse out. So information about that is going to spread, and eventually the parallel components everywhere are going to be on average the same, and so this information would have completely diffused out classically. On top of that, of course, even for this model, you're going to have a spread of entanglement. So this generic model, this kind of generic Heisenberg model, is one in which you both have a spread of classical information, and you also have a spread of quantum information in the form of the entanglement growing as a function of time. And so you can ask, well, how do both of these things play out? I mean, which one is growing faster? How does each one of them grow individually? So this is also a difficult thing to calculate explicitly to obtain any analytical results for, because this Hamiltonian, like the one with the z components of the spin, in some sense was hard enough, and now of course you have all the components of the spin, so even calculating the unitary for this Hamiltonian is difficult. And so what you have to do is you have to resort to numerics, and so I'll show you some numerics now, some numerical data on these kinds of Hamiltonians. And the reason that I say these kinds of Hamiltonians is that even though I've used this Heisenberg model as an illustrative example of a system in which you have a spreading of both classical and quantum information. When people do numerics, this is not the kind of Hamiltonian that they often work with, and there's a very good reason for that. So the reason for that is that if you were to look at, for instance, the simplest kind of Hamiltonian that is in this family. So if I assume that this J, the coupling, is only confined to nearest neighbors. Now suppose I did that, right? And my spins were spin half quantum objects. Then it turns out that there is actually something rather atypical about the Hamiltonian that you get. So the nearest neighbor one-dimensional Heisenberg model for spin halves is what's called an integrable model. It just happens to have a very large number of conserved quantities, not local conserved quantities like the earlier Hamiltonian that we were looking at. So in the earlier Hamiltonian, the Z component of the spin at every site was conserved. So you actually had a conserved quantity at every site, strictly localized to every site. If you look at the nearest neighbor Heisenberg model for spin half, it turns out that again you have a very large number of conserved quantities, a number of conserved quantities that scales with the system size, but each of those conserved quantities is not strictly localized anymore. So the conserved quantity itself is extensive in some sense. Nevertheless, the existence of these conserved quantities gets in the way of this spread of classical information, and so that model is not representative of what happens generically. So if you want to look at models which are more generic, you have to move away from the simplest case of the Heisenberg model, at least if you're confining yourself to spin halves, because spin half is sort of the easiest thing to treat numerically. And so the model that I'm going to show you, for which excuse me, this kind of spreading has been calculated numerically, is the one which is on this slide. And so you can see that this model, so if you just look at the Hamiltonian here, right? If you didn't have the first term, if you had only the other terms, then of course it would look a lot like the kinds of Hamiltonians that we've been discussing before. It would only have these SZ, so again it's a one-dimensional system of spin halves, and so you have a spin half at every site. And so if you didn't have the first term, then of course it would be like, whatever we discussed earlier, and you would again expect to see some logarithmic growth of the entanglement and no spreading of classical information. But the first term is the one which actually prevents that from happening, because that involves an SX. And so because there's an SX in the first term and everything else has SZs, the individual SZs don't commute with the Hamiltonian anymore, because they don't commute with the SX. So this model, even though it doesn't look anything like the Heisenberg model, actually does have the generic features that we're interested in, which is basically looking at a Hamiltonian which doesn't have this conservation of individual S sets. And this is a very simple model which does that. And so in this paper, the spread of classical information and quantum information was obtained numerically. So let me just tell you a little bit about exactly what was done. So as far as quantum information is concerned, it was again, so they looked at the entanglement as a function of time, starting from some product state, much like what we did here. And what you can see from the numerical results here is that for this model, the entanglement actually grows ballistically, meaning that the entanglement as a function of time is linear in time and not logarithmic. So this is on a log-log scale, and here the red line is the linear fit, and you can see that the linear fit actually fits pretty well over about a decade or so. So for models like this, it turns out that you don't really have, when you're doing the numerical calculation, as much of a dynamic range in time as you have for these Ising type models. Nevertheless, given the range over which the calculation is possible, you actually do have this linear increase in the entanglement. So the growth of entanglement is ballistic because it's increasing linearly as a function of time. As far as classical information is concerned, the way that its increase was calculated in this particular piece of work was to look at how energy spreads diffusively. So in the discussion so far of the spread of classical information, I was giving you this example of having a large in-plane component of the spin and then seeing how that would diffuse out. So in this model, it turns out that a more practical thing to look at is to start with an initial state in which you have a large energy density in some particular part of the system, and then let that state evolve as a function of time and see how the energy is spreading diffusively. So, so basically what you're doing is you have this whole sort of a blob of energy at some particular site, let's say site 0, at time t equal to 0, then you let the state evolve, and what will happen is that the blob is going to get wider and wider. And so you can look at how the width of that blob increases with time, the width of the blob over which the energy is concentrated, how that width is increasing as a function of time, and that's what they've done here. And what you find is, so r of t is like that width, so r as a function of t, and you can see that the best fit here is a fit to square root of t, and this is characteristic of diffusive behavior. So in this sort of generic kind of spin system, what you find is that classical information in the form of the spread of energy is something which is spreading diffusively, whereas the quantum information is actually growing ballistically. And so this is sort of the generic thing which happens for systems of this sort, that you do have a spread of classical information, and usually that classical information spreads ballistically. You have diffusion in the system. Diffusion, the existence of diffusion in the system is related to the system thermalizing, reaching thermal equilibrium on its own. But at the same time, the entanglement grows faster. It actually grows linearly. And in fact, the generic growth of entanglement in many body systems of this sort, spin chains and things like that, is actually a ballistic growth of entanglement. And we'll also look at the ballistic growth of other things in the subsequent lectures. Now, I also wanted to draw your attention to this other numerical calculation. So it turns out that if you want to look at a logarithmic growth of entanglement as a function of time, then the kind of Hamiltonian that I wrote down is, of course, the best, is a prototypical example of a system in which the entanglement growth is logarithmically with time. But you can also have other Hamiltonians which are not just Hamiltonians which are functions of S, Z, but which also involve the other spin components, where again the entanglement can grow logarithmically. And this is an example of such a Hamiltonian. So you can see that this is a Hamiltonian which has, there's a typo here, there should be YY. So it has a coupling between the X components and the Y components and the Z components, all nearest neighbor. But additionally, there's also a term at every site which couples just to the Z component of the spin, and that term is random. So this is basically what's called an XXZ model with a random feed. So it has couplings between all the components of spin, nearest neighbor couplings, and on top of that, you also have a random Zeeman field at every site. So it just turns out that if the randomness is sufficiently large, if you draw this from a random distribution with a sufficiently large width, then once again, even though you have couplings between all components of the spin, you can actually have a logarithmic growth of the entanglement entropy and a saturation to a value which is linear in the system size. And so, so this is actually an example of a system which undergoes what's called many-body localization, but I'm not really going to talk about many-body localization in this series of lectures. It's a very interesting topic in its own right, but maybe something that's appropriate, for a whole lecture series devoted to it. So all that I wanted to show you here was that even in this system, you can have an entanglement growth which is logarithmic, but the difference between so that's one thing, and even in this system, there really is no spreading of classical information. So if you were to try to calculate how classical information in this system spreads by doing something similar to what I showed you earlier, let's say how energy spreads or some particular component of spin spreads, you would see that that spread is actually subdiffusive, that you wouldn't see diffusion here. but you will see a logarithmic growth of entanglement. It turns out that there are also other systems which are similar to the kind of system that I just showed you, where again you can have some interesting growth of entanglement. So here is another system which I looked at with my student many years ago, where what happens is that you do have an entanglement which actually grows linearly with time as opposed to logarithmically with time. But if you look at the spread of classical information, if you look at how, say, an energy spreads, energy packet spreads as a function of time, or something else spreads as a function of time, something that's classical, that's actually subdiffusive. So unlike what I showed you in the previous slides, where you either had, for the generic case, diffusive spread of classical information and a ballistic spread of entanglement, or in the previous slide you had a logarithmic growth of entanglement and subdiffusive spreading of classical information. This is an interesting system where it appears that the classical information as quantified by this kind of transport is subdiffusive, but the growth of entanglement is actually linear. And so there's still speculation on exactly what kind of system this is, what actually causes this. It appears that this sort of system is perhaps neither fully thermal, meaning it's not something which is like, say, the generic kind of system which reaches thermal equilibrium on its own, nor is it really many-body localized, such that you have a logarithmic growth of entanglement. It's something that's in between. And some people, there are many different names that people give this kind of system. So one of the names that you might find in the literature is a non-ergodic extended phase. It has some features of a system which thermalizes, meaning that the entanglement is growing linearly as a function of time. But then because of the fact that classical information is subdiffusive, it's also not fully ergodic. It's not something which would really thermalize, and so it is non-ergodic. So I thought I'd just mention this as an example of a system in which you have, okay, so I think that's...
A quick question. So regarding these kinds of systems, is there some more current understanding which says whether these weird phases can survive in the thermodynamic limit, this half and half kind of a thing?
Okay, so that's a good question. Short answer is no. The slightly longer answer is that there's probably no better understanding of whether these phases survive in the thermodynamic limit any more than there's any understanding of whether even MBL survives in the thermodynamic limit, right? But certainly, right, but I think the understanding of what happens in the thermodynamic limit in these phases currently is much less than what was known for MBL systems. Like for MBL systems, there's speculation that there's a pre-thermal phase, and then there's really a thermodynamic limit MBL transition, there's a finite size MBL transition. For these systems, they haven't really been investigated to that extent. I mean, the one thing that I should say about these systems is that here the field, the Zeeman field at every site, is actually not drawn from a random distribution, but is a deterministic quasi-periodic potential. So some of the arguments that are generally put forth in order to say that MBL doesn't exist, which have to do with the specific nature of the field at every site being random, those arguments don't apply to a system like this. And so some of the instabilities that you might talk about for an MBL system, which have to do with rare resonances and so on, will not arise here. But then, but this in some sense is a priori an even more fragile phase. And so whether even in the absence of those resonances this thing can survive is something which...
No, okay, perhaps the reason I was asking whether it survives with the thermodynamic limit is, I mean, if you look at things like level distribution, there are two limiting cases, like a Poisson and a Wigner-Dyson.
Right.
But this is something like halfway. So how can that kind of a level distribution stabilize?
Well, okay. So here there are two things. So if you look at the, so there are two aspects of this. One has to do with the entanglement entropy being growing, linearly with time. And if you also were to look, so this is of course starting from an initial product state. if you were to look at the entanglement entropy of individual eigenstates of this system, you would find that the entanglement entropy of individual eigenstates is also a volume law. But it turns out that if you were to calculate the entanglement entropy per unit length, that would be subthermal. So you have non-ergodicity and you also have, but you have extensiveness. And if you ask, well, which one of these is related to the energy level spacing statistics, right? So it turns out that the energy level spacing statistics is actually related to the non-ergodicity. So you will see that the energy level spacing statistics of these systems is not consistent with random matrix theory, even though the entanglement entropy of the eigenstates is volume law. Okay, so anyway, so I'm out of time, so I'll stop here. So this basically concludes what I wanted to tell you about quantum dynamics versus classical. Yeah, sorry.
Then go up to 10:55.
Oh, we started? Okay, fine. But anyway, I mean, as far as this particular module was concerned, this was essentially all that I had to tell you. I could start the next module now, or I could just start it, with my next lecture. But the thing which I want to, so to conclude this discussion, what I wanted to show you was that there is a difference between what you would call classical information and what you call quantum information, and the way that these things spread in models. So for most of the time, we looked at a fairly contrived model in some sense, in which there was absolutely no spread of classical information, but you did have a spread of quantum information in the form of the growth of entanglement, a rather slow spread of quantum information because the entanglement grew logarithmically. Then, of course, towards the end of this lecture, we looked at more generic models for which it's harder to do any kind of analytical calculation. But for these generic models, you have a growth of both, a spread of both classical information and of quantum information. And the spread of classical information is diffusive, which is really the usual situation for models which are not special. And there is still a growth of quantum information, which is actually faster than in the model that we considered earlier, which is a ballistic growth here as opposed to a logarithmic growth. So in general, of course, there are arguments which seem to suggest that the entanglement entropy would always grow faster than any spread of classical information. So it wouldn't be possible then to come up with a model in which, let's say, classical information is spreading ballistically, but the entanglement entropy is growing logarithmically. So there are some general arguments that people put forth, and there are also arguments related to how fast the entanglement entropy spreads, related to something called Lieb-Robinson bounds. And so I think, again, Michael Kastner in his lectures already mentioned the Lieb-Robinson bound. So we will also look at some consequences of the existence of Lieb-Robinson bounds in the next lecture, in the lecture after that, not in the context of the spread of entanglement, but rather in the context of looking at how chaos spreads in quantum mechanical systems, what that means, and what kind of bounds you can place on how fast chaos spreads and how large Lyapunov exponents can be, and so on. So that's going to be the topic of my next lecture, which is in the afternoon today, and also some part of the lecture after that. So what we are now going to do is we are now going to investigate other facets of dynamics. So one of the most ubiquitous things with classical dynamics, when you have many degrees of freedom, again the generic situation, is that this kind of dynamics is chaotic, meaning that there's a strong sensitivity to initial conditions. And the reason that I say that that's a generic situation is that generically you have more than one degree of freedom, and generically these degrees of freedom, the way that they interact, if you write down a Hamiltonian, generically would have some nonlinear terms. So a combination of having more than one degree of freedom, having say several degrees of freedom, and also nonlinearities in the couplings between these degrees of freedom. So this combination usually gives you a strong sensitivity to initial conditions, which is what we know as chaos. One should of course be very careful in using the word chaos, because strictly speaking, mathematically there are many different definitions of what chaos is. There's a whole hierarchy of how systems can be chaotic, what different diagnostics are for chaos, and those fall into a nice hierarchy. For us, at least for the next lecture and the lecture after that, our main defining feature of chaos is going to be the sensitivity to initial conditions. For a classical system, we are going to assume that there is a phase space in which you can look at the evolution of the system, and the sensitivity to initial conditions can be quantified by looking at a divergence of trajectories in phase space, looking at the distance between trajectories in phase space and how that changes as a function of time. And so for us, chaotic systems are going to be those systems for which, when you start with some arbitrary initial condition, two arbitrary initial conditions which are very close to each other, and you look at the evolution of the trajectories are going to diverge in such a way that the distance between them, the Euclidean distance between them, increases exponentially, and the coefficient sitting in the exponent is an important quantity, so that's called the Lyapunov exponent. So for us, at least, chaos would mean a non-zero positive Lyapunov exponent, classically. And so what we're going to do is we're going to see how you can generalize this idea to a quantum system. Now, you can immediately see that one of the problems with doing this for a quantum system is that there isn't really a phase space in which you can talk about well-determined trajectories because of the uncertainty principle. So imagine that the system in question was, okay, now let's just think of a system with many, many degrees of freedom. So suppose you have particles in a box which are interacting with one another. So this is basically like, like a gas or a fluid in a box. So classically, if you were to look at this system, you can of course talk about the state of the system at any instant of time as a point in phase space. So if you have n particles, then you know that the phase space is 6n dimensional. Every particle has 3 components of position, 3 components of momentum. So there's a 6n dimensional phase space. And you can look at the evolution of this isolated system in terms of a trajectory in phase space starting from some initial point. And so you can also look at 2 initial points which are very closely spaced, the evolution of the trajectory, calculate in principle the Lyapunov exponent, and so on. Now, if you were to try to import this idea to quantum mechanics, if you were to now look at again the same system of particles in a box, but now quantum mechanically, then you know that the uncertainty principle immediately tells you that there is no well-defined notion of a phase space. You cannot simultaneously specify all the components of position and all the components of momentum of a single particle. And so then either you're going to have to deal with trajectories in phase space which are not really well-defined trajectories, or phase points which are not really well-defined phase points but have some kind of spread due to the uncertainty principle, or you're going to have to completely look at this in a totally different way, like not think of it in terms of a phase space at all. Think of something which replaces the notion of a phase space for a quantum system, and then sort of try to look at chaos from that point of view. So we are going to look at sort of a combination of both, more the latter than the former. So what we'll see is, so what we try to do is we're going to try to determine and calculate Lyapunov exponents for quantum systems, despite the fact that those systems have these limitations. So we'll see how that is done. And in doing that, we will come across this quantity, which is called the out-of-time ordered correlator, or OTOC for short, which is really going to be the main physical quantity to calculate for a quantum mechanical system in order to extract Lyapunov exponents. Okay, thanks. So, and if you have any questions, please feel free to ask.
I have a question. So, if you go back to the Burdenson's slide.
This one, or?
No, the first one. The first one. Yes. So, in this case, if I look at the level statistics, it's going to be Poissonian.
And entanglement entropy, what?
No. If I look at the level statistics for this particular Hamiltonian.
Okay, yeah. If you, right.
It's going to be Poissonian?
Yeah, if you look at the level statistics of this particular Hamiltonian, yes. I mean, this is a completely integrable system. So yeah, so it's going to be Poissonian.
What I'm trying to ask is this growth of logarithmic logarithmic growth of entanglement entropy.
Yeah, so the logarithmic growth of entanglement here has to do with the fact that these couplings are falling off exponentially. But suppose you picked some other form for the couplings, even then, of course, your level spacing statistics would still be Poissonian. That has nothing to do with the specific form of the couplings. But the growth of entanglement as a function of time would not be logarithmic anymore.
So let's say, so what I'm trying to ask is this. So if I take, let's say, this sort of couplings, but my Hamiltonian is a non-integrable Hamiltonian.
Okay.
So then I do not expect the entanglement entropy, the growth to be logarithmic.
No. So the main point here is that, okay, so an extreme example of that is actually what I showed you here, right? So here you can see that the couplings are the only coupling that you have is a nearest neighbor coupling, which is even more short ranged than an exponentially, falling off, something that falls off exponentially. And you can see that the entanglement is growing linearly here. So in some sense, here what's happening is that your coupling is even more short ranged than something which falls off exponentially, despite that the entanglement is still growing faster, right? And that actually has nothing to do with, for a Hamiltonian like this, the range of your coupling. The fact that the entanglement is growing ballistically now simply has to do with the fact that you don't have all these conserved quantities anymore. So you get rid of the conservation laws, your SIZs are no longer conserved at every site, and you also, as a result, have a spread of classical information. That fact alone is enough to make the entanglement grow linearly as a function of time, regardless of what you're doing with the couplings.
Hello. Are there any further questions? So if not, let's thank the speaker.